video to help you through the activity on the gas laws. The gas laws tell you a mathematical relationship between pressure, temperature, and volume of a gas. And the gas laws basically tell you that the pressure times the volume of a gas divided by its temperature will always be a constant number. And so if you change one of the things, then you'll still get that number. The combined gas law tells you how to calculate the pressure, volume, or temperature based on a change in one of those three things. This means that the first pressure, volume, or temperature is going to be equal to a constant value. And the second pressure times its volume and divided by its temperature will be equal to the same value. And so these things can be written equal to one another. There are two main things that you need to get out of today's activity. One is how to use this combined gas law to do calculations. And the second is to get a conceptual understanding about the properties of gases. The first thing I'd like to demonstrate is that all gases behave the same way when they're behaving ideally. Here are two scenarios. This is scenario A in your activity, and I'd like you to fill in the table with the pressure and the temperature of these two gases. There are the same number of molecules in each box. They're at the same temperature. And although their pressures are fluctuating slightly, they're both averaging around 0.25 atmospheres. When you have the same number of molecules in a box like this, they will exert the same pressure on the box despite the different size or shape of the gases. This is how ideal gases behave. They behave the same way despite their identity. The reason is because they don't touch each other for most of the time. Only when they bang into one another do they even know that other gas molecules are around. But because they spend most of their time not interacting with other gas molecules, it doesn't matter what their identity is. The size and shape of the gas molecule doesn't matter. So equal amounts of a heavy or a light gas, or a large or a small gas, will give you the same pressure. Treat all gases the same and assume that they are ideal. And in general, real gases behave as ideal gases unless they are at very, very low temperatures where the molecules are closer together, or very, very high pressure where the molecules are closer together. Under normal circumstances, gases behave ideally and it doesn't matter what their identity is. Let's look at scenario B. We're going to double the amount of gas in the second container. And what happens here is that we're going to end up doubling our pressure. Notice that the temperature doesn't change when I add more gas molecules, but the pressure does change. I started out around 0.25 atmospheres. My pressure is fluctuating, but the average is around 0.25 atmospheres. The pressure in the container with double the amount of gas molecules is twice as much as the original container was. It's around 0.5 atmospheres. When you double the amount of gas at a constant volume, you double the pressure. And you might have seen this if you added air to a bike tire. The bike tire is not very flexible. And so when you're putting air in a bike tire, you're adding molecules of gas and increasing the pressure. If you double the amount of gas molecules, you'll double the pressure. Now, this does not apply to our combined gas law equation because you're changing the amount of gas. In the combined gas law, you're assuming that the amount of gas is staying the same. So don't try to apply the gas law to this particular situation where the number of molecules is changing. Now let's look at a third scenario. In this one, we're going to double the temperature. Notice I'm adding fire to the bottom here to increase the temperature in the second container. The volume is staying constant, so I'm essentially heating a sealed container. And notice that the pressure is increasing. I started off at a pressure of around 0.25 atmospheres, and now that I've doubled the temperature, I'm around 0.5 atmospheres. Doubling the temperature will double the pressure. And this is why we don't heat sealed containers in the chemistry lab. If the pressure raises too much, the container could burst. Now let's look at another situation where we're going to reduce the volume at a constant temperature. So when you reduce a volume of a sealed container, you would actually increase the temperature. But we've added a cooling mechanism here so that we can keep the temperature constant. So we've compressed a gas. Notice that when we reduce the volume by half, we double the pressure. Here, we started out close to 0.3 atmospheres and we ended up close to 0.6 atmospheres. When we reduce the size of the container by half, then we double the pressure. This fits into Boyle's law. Now, it's not important that you remember this particular law is Boyle's law, but please notice that it's familiar. The only difference between this and the first equation I showed you is that temperature is not part of this equation. But I could have divided each side of this equation by temperature, and I would have come to the combined gas law. But if I'm at constant temperature, that means that the temperature on both sides would be the same, and I could multiply both sides by the same number, and I would end up with this equation. When something is constant, you can simply drop it out of the equation for the combined gas law. Once again, it's not important to know that this is Boyle's law. In fact, you could have replaced this equation with the combined gas law and just noted that the temperature didn't change. When you halve the volume, the pressure doubles. For a real-life application of this, think about what happens when you compress the plunger of a syringe if the plunger was sealed. Here's a picture from your textbook where the syringe is sealed with a cap. If you start out at an initial volume, let's say 3 milliliters, and you compress the syringe so that the plunger now is at 1.5 milliliters, you would build up pressure in here, and you could actually feel it pressing against your thumb, or if you were holding your finger over the nozzle here, you could feel it pushing against your finger. When you halve the volume, you double the pressure. And if I was going from 3 milliliters to 1 milliliter, I would triple the pressure. When you decrease the volume of a sealed container, you will increase the pressure. Okay, let's look at one more example. Here's a scenario where I'm going to double the temperature. So I'm going to heat up this container. But this container has elastic walls. So this is kind of like a balloon. If I were to heat up the air inside of this balloon, what would happen? Well, it's right in front of you. When you heat up a gas, the gas molecules expand. They get farther away from each other. And so if you're in an elastic container like a balloon, the balloon would expand. Or in this case, the container gets bigger. This is what happens when you increase or change the temperature at a constant pressure. When I increase the temperature at a constant pressure, I end up having a container here that's twice as large as the container that I started with. Or if you think of this, where I would go from this situation and reduce the temperature by half, my container would decrease by half. If I took this balloon from inside, where it's warm, to outside, where it's very snowy and cold today, the size of the balloon would decrease. If you're not sure about this, try it. This obeys Charles' law, and Charles' law is just part of the combined gas law that focuses on the volume and temperature change at constant pressure. In this case, we are at constant pressure. So basically, you're allowing the pressure on the inside and the outside to be equal by expanding or contracting the size of the container. So even though you could put pressure back into this equation, you don't need to. It doesn't change, and so it would drop out of the equation. It's not important for you to know that this is Charles' law. It's only important for you to recognize that this is part of the combined gas law. Here's Boyle's law and Charles' law written again, along with the combined gas law. It's not important for you to know that this particular one is Boyle's law or that this particular one is Charles' law. These are two laws that were developed in the 1600s by two independent scientists, and their names are attached to those laws. But later they realized they were really studying the same thing. They were studying the effect of pressure, volume, and temperature on a gas when the number of molecules was kept constant. This is called the combined gas law. If you just remember the combined gas laws, then you already know this relationship and this relationship. Anything that stays constant can be simply dropped out of the combined gas law to get Charles or Boyle's law. Whenever you're doing calculations with any gas laws, the temperature must be used in Kelvin. If you use degrees Celsius or degrees Fahrenheit, you will not get a correct answer. In Kelvin, your temperature will always be a positive value, but in degrees Celsius or degrees Fahrenheit, you can have 0 or negative values. And if you have 0 or negative values for the temperature, you can get some really wacky results for pressure and volume. So remember that anytime you're doing calculations with the combined gas law, the temperature must be in Kelvin. As far as the other units go, it doesn't really matter as long as you use the same units on both sides of the equation for pressure and volume. Understanding the relationship between pressure and volume can help you understand how breathing works. You breathe by lowering the diaphragm and expanding the volume of your ribs. What that ends up doing is lowering the air pressure because you're expanding the volume of the container. And that lowers the pressure just temporarily. Since your lungs are not a sealed container, then gas will fly from the outside into the inside to equalize the pressure. You can feel the lowering of pressure if you try to breathe in while closing your mouth and nose. You can feel the reduction in pressure in your lungs. When you breathe in, the pressure is equalized immediately because gas always flows from high pressure to low pressure. So when you breathe in, you're increasing the volume of your lungs, it temporarily lowers the pressure in your lungs, and gas flows from the outside to the inside, from higher pressure to lower pressure. Breathing out is opposite. You contract your diaphragm or move the diaphragm up, and it makes the volume of your lungs smaller. This instantaneously increases the pressure in your lungs. You could feel this pressure if you close your nose and your mouth and try to breathe out. You can see or feel that you increase the pressure in your lung cavity if you try to breathe out while closing your mouth. But your lungs are not sealed like this most of the time, and so the temporary increase in pressure in your lungs is removed by letting gas flow out of your mouth from the higher pressure in your lungs to the lower pressure outside. This is how we move gas to breathe. In an upcoming activity, we will also discuss how gas pressure allows oxygen and carbon dioxide to move between your lungs and your blood in a way that helps you get oxygen into your blood and carbon dioxide out. But we'll leave that for another day. It's important to understand atmospheric pressure. Sea level is 1 atmosphere. It literally means that there's 1 atmosphere above us. There are some equivalent units that you should know, and those are on the first page of your activity. 1 atmosphere is equal to 760 torr, 760 millimeters of mercury, or 14.7 pounds per square inch. In other words, the force exerted on us from the atmosphere above us is the same as the force that would be exerted if you put 14.1 pounds on 1 square inch. It's a lot of pressure. The higher you go in the atmosphere, the lower the pressure is. And if you go lower than sea level, so under the sea, then you also have the water on top of you. So pressure increases going down and decreases going up. You might have felt this if you ever climbed a mountain in Colorado, or if you've ever been in an airplane and gone up to high altitudes. You can feel the drop of pressure, usually in your ears, and sometimes people get altitude sickness if they go from low elevations to high elevations because there's lower oxygen content in the air at high elevations. Thanks for watching this video on the combined gas laws. Please make sure you finish the conceptual questions and the questions that apply the combined gas law. If you have any questions, feel free to post them in the comments. And if you liked this video, let me know by giving me a vote.